This is 3211. And it says you have an inductor, an inductance L, and it says the EMF, or the self-EMF in this inductor for some time is E, EMF e to the minus kT. Basically says the EMF across this inductor undergoes exponential decay. And this is what really happens if you just have an EMF and you just let it go. So we talked about how to build up an EMF in an inductor in a circuit. When we throw a switch, when we turn off the switch, something like this happens. You have exponential decay. The question is how much charge flows through some point in the inductor. So let's say it doesn't really matter any point here. How much charge passes that point as this thing decays, or as the current dies down. So to solve this requires a little bit of intuition and a lot of calculus, unfortunately. So what we're going to do is first apply a little bit of intuition. We know we have an EMF across this inductor and it's going down. Therefore, we also know we must have current flowing through the inductor. There's an EMF across it. There must be current flow. It must be building a magnetic field to counter the field created by the current, which is why the EMF goes down. Let's see, what else do we know? We know then that the way to get the amount of charge that goes past that point is first to get the current. So we need the current before we can get the charge. So we have to look at this and figure out how we get the current. Well, we go to essentially our definition of the inductance, and that is that this is also equal to then minus L di dt. So we set this E naught e to the minus kT equal to minus L di dt. Because once we know the current, we can figure out how much charge flows past one point. So let's see. So to get the current, we're going to have to integrate because we have differentials here. Whenever you see sort of differentials in time and differentials in something else, if you can, you get them on the same side, or you get them on opposite sides. So here, it looks like it'll work out if we just pull the dt over here, and we have all the stuff related to t here, and we just leave di there. So that's what I'm going to do in the next step. This will come over here, we'll pull the L over, pull the negative sign over, so we're just going to be left with di on one side, and the other will be minus E naught over L, e to the minus kT dt. So we've turned this into an equation that we can integrate. Okay. Now, it helps to integrate it actually a couple times, a couple different ways. First, let's use this integral to figure out what the initial current is. Okay. So let's ask ourselves, when this starts at time equals 0, and t equals 0, this e to the 0 is 1. So at the beginning it has an EMF E naught. So let's figure out what is the initial current. Okay? So let's integrate both sides and see what we get. Well, in addition to integrating, we've got to think about the boundaries of the integration. So at the beginning, it's going to go from some current I naught and then go down to 0. Right? So if the EMF is going to go to 0 at large t, this exponential decay to 0. So if the EMF goes to 0, the current must go to 0. So it must go from I naught to 0 in time 0 to infinity. That's why I would set that up. Okay. And this integral of di is I. You evaluate it at 0. You evaluate it at I naught. So you end up with minus I naught, just because that's at the bottom of the limit. And then here, we need to integrate this. It's just the integral of an exponent, so you divide by the derivative part, you divide by negative k. K comes here, makes that positive. You get epsilon, E naught over KL, and then you just repeat the expression, e to the minus KT, and then you apply the limits from 0 to infinity. So what you end up with then is here we have minus I naught equals E naught over KL. And we're going to pull this out and do the limit just on the exponent. E to the minus infinity is 0. E to the minus something is 1 over something, e to the something, and e to the infinity is a big number. So 1 over a big number is 0, so that's 0. Minus e to the 0 is 1. So that minus 1 cancels that minus 1. You see that I naught is EMF naught over KL. It's I naught. But really, to figure out how much charge flows by here, we need the current as a function of time. We need to know not just how much do you initially have, the question was what is the total amount of charge? How much current is a function of time? So for that, we have to basically evaluate this integral again. It was when we evaluated the integral over a certain limit that we just figured out I naught. Here's another way. Here's another limit you could have used. If you want it as a function of time, you would say the integral is going to go from I naught to some current I. I is a function of time. This is the initial, and this is how it varies with time. di equals the integral, and again, it's going to go from time equals 0, but to what? To time t. At some time t, it'll be a current I. And then it's the same integral. EMF naught over KL, e to the minus kt dt. And here's something we do in physics and calculus. We don't want to mix up the t we're integrating with the t that we're applying limits for. So we put a prime here. Whenever you see a prime like that, you're just trying to keep it straight in your head. You're integrating with respect to this time, and then in the end you're getting something as a function of time through your limit. So often we put that on there. This becomes what? This becomes I as a function of time minus I naught equals this. So we already evaluated it here. It's basically this same thing with these limits. So it becomes EMF naught over KL times what? Let's see, times e to the minus kt, but at the limit, or at the boundary t. So it's e to the minus kt. Minus e to the minus kt evaluated at 0 is still 1. Okay. And now we're going to move this up top and keep going. Okay, so we have put our expression for I up here. Now there's something important to notice. The reason we calculated that I naught is you see it actually shows up here. Okay? The EMF, the original EMF over KL is really I naught. So we're just going to replace it right there. And then you see when you do that, things start to cancel. You see that this is just something minus I naught, and this is something minus I naught. Yeah, I naught times 1. So the two ones that are added in there go away. So we get the current as a function of time basically just goes through exponential decay, just like the potential, or the EMF as a function of time goes through exponential decay. But the current as a function of time was not the question. The question was the charge. How much charge passes that point? Well, the answer is finite because we start with some current, and the current goes to 0. See, at infinite time, this term will be 0. So how much charge passes from when the current goes from I naught to 0? Well, you just, again, use a derivative and write a definition. You can say I naught e to the minus kt. What is I naught? It's dq dt. Current is the flow of charge, dq dt, past some point, charge per unit time. And then you do the exact same thing. We bring the dt over. We say dq equals I naught e to the minus kt dt. We integrate both sides. And this time we're going to go from time equals 0 to infinity. And that means the charge that crosses will go from 0 to some charge q. We say at time equals 0, no charge has crossed yet. And it goes to some charge q total. So the integral dq is q minus 0 is q. So that's the easier integral. This is q, I'll write total here. This is not as a function of time. And this integral is, let's see, so to integrate e to the minus kt and divide by a minus k. So it's minus I naught over k e to the minus kt evaluated from 0 to infinity, which is minus I naught over k e to the minus infinity is 0 minus minus e to the 0 is 1. So those two negatives, negative 1 times negative 1 cancel. So total charge it crosses is just I naught over k. But if you wanted it in terms of the given variables, we again remember what is I naught? I naught is the EMF not over KL. So over another k, final answer is the original EMF over k squared L is the total charge that passes that point.